Welcome back to Carneades.org. Today we're going to be continuing with our series, You Can't Handle the Truth! In this video, we will be finally looking at Axiomatic Theories of Truth. Now, in this video, we will start by looking at the motivations for Axiomatic Theories of Truth. Then, we will cover the distinctions between axiomatic and semantic theories of truth. And then the distinctions between typed theories of truth and type-free theories of truth. Note, we're not going to actually be covering type-free theories of truth in this video. We will save that for the next video. After that distinction, we will explain some of the notation needed to understand these theories. We will be building on a lot of the logical notation we've used in previous videos and adding more. After that, we will provide the axioms for one specific typed theory of truth, and then two ways that we can expand that typed theory of truth. And then in the following two videos, we'll cover, in each one, two type-free axiomatic theories of truth. Now, before we get started, type theories of truth are closely tied to Alfred Tarski's theories of truth. We will also be using piano arithmetic in this video. If you're not familiar with these two concepts, I encourage you to watch the videos which precede this one in the series, particularly the one on Gödel numbers, for some background. You will not need to understand everything in those videos, but they will provide a good background to what we're going to be discussing here. If you already have a good sense of kind of some of the logical mechanics that have gone into those things, you understand a little bit about Tarski's theories of truth, or you've just watched the videos, let's get started. So, Alfred Tarski proved that, given certain conditions for a formal system, truth cannot be defined. In response to this, many philosophers have argued that truth should be taken as a primitive predicate. What we mean by a primitive predicate basically is a predicate that we're not going to offer a definition of, that we're just going to take as basic in some way, and we're just going to explain the ways in which it can be used. And our focus should be on the axioms which determine how to use truth, not a definition of truth. Taking truth as primitive will avoid many of the problems that we've run into before when it comes to truth. And many deflationists, in particular, will take this route. If you don't know what deflationism is, check out the video earlier in this series. However, using axioms to explain how truth functions will come with its own set of problems. So, the axiomatic theories of truth will sometimes have the same problems as Tarski's theories of truth. They may take on other problems from deflationary theories of truth, or in the case of type-free theories, may have their own set of problems altogether. To put it another way, there are basically two ways to respond to this problem of the indefinability of truth within a given language. Either we can use a meta-language, as Tarski does, or we can take truth as primitive and define its role by the use of axioms. The first route is known as a semantic theory of truth. That's what we've covered in our Tarski's theories of truth. The second is known as an axiomatic theories of truth. Both of these different kinds of theories are going to work together towards similar goals, but they're going to do so in different ways. Basically, our semantic theory of truth is going to focus on kind of meaning and offering definitions through meta-languages, while the axiomatic theory of truth is not going to cover meaning at all, take truth as primitive, and just give us the ways that we can use truth. Alright? Now, within axiomatic theories of truth, there are two different theories that I've already mentioned a bit of. They're called typed theories of truth and type-free theories of truth. The former separates truth bearers by type, and does not allow for any truth predicates to be predicated over itself. And this is going to be the way that they're going to avoid things like the liar's paradox. If you can't have a specific truth predicate be predicated over itself, then you're not going to run into those problems, in very much the same way as Tarski's hierarchy of languages avoided the liar's paradox by having that kind of level of languages in the meta-language system. I, of course, have some objections to this, but check them out in the video on Tarski's theories of truth. The latter, the type-free theories of truth, allow for a particular truth predicate to predicate over itself, and in turn need to find new and different ways to kind of solve the liar's paradox that's going to arise from that. We're not going to cover type-free theories of truth in this video, but we will in the following videos. Before we start with the axioms about truth, we're going to need a base theory. Think of a base theory as a series of truth bearers as well as kind of the mechanics or the basic logic behind them. It's a description of what kinds of things the truth predicate can apply to and how they function. Instead of taking propositions as our truth bearers or sentences, we'll have truth now apply to numbers. What kind of numbers, you ask? Specifically, Gödel numbers. These are numbers which are basically coding a specific proposition in logic speak. So we have specific numbers which represent those specific elements of a logical statement. For more on Gödel numbers, check out the video on what are Gödel numbers. There'll be Gödel numbers that represent specific sentences in a particular language. And this language and kind of the mechanics of it is also going to be considered part of our base theory. What language are we going to use, you may ask? The language we'll use is the language that we used in the video on Gödel numbers, but with the digits replaced by the successorship operator from Peano arithmetic, and the axioms of Peano arithmetic added in. What do I mean by the digits being replaced by the successorship operator? So you remember in the previous video on Gödel numbers, we had a codification for 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. In Peano arithmetic, we learned about a different way to represent numbers. Instead of using digits, we just use successorship. So 1 is the successor of 0, 2 is the successor of the successor of 0, and so on and so forth. To limit the number of symbols we're using, we're just going to use a bunch of successorship operators to represent numbers instead of digits. It's going to make our numbers a lot longer, but limit the number of symbols we're using. And we'll talk a lot about this as we move forward. We're going to refer to this language as TPA, Truth Peano Arithmetic. We will use a meta-language to talk about TPA, and we'll call it MPA, kind of the meta-language of Peano arithmetic. This meta-language is also the language we're just generally discussing in. And because we're not talking about Tarski, or we're not using Tarski specifically, we're not going to talk too much about meta-languages and object languages. But to get a basic sense, we're going to now add some, not all, but some of the notation that's going to be necessary here, both in MPA and TPA. So in MPA, we have capital X, Y, and Z, which are each going to represent a sentence of MPA. They're going to be variables that stand in for a sentence. And since MPA is a meta-language of TPA, they might also be sentences of TPA. And then when we put these kind of square brackets around one of those variables, it's going to be a translation of X into a Gödel number in TPA, so long as X is a sentence of TPA. It's not going to translate if X is not a sentence of TPA. Hopefully that makes sense. Now, ST, lowercase t, X means that X is a number of TPA to which the predicate T can be applied. Remember, our truth predicate, our T, truth predicate, is going to apply not to words, not to logical symbols, but to numbers. So STTX means that X is a number of TPA. It's a Gödel number which T can be applied to. It doesn't necessarily mean that that number represents a true statement, but it's the kind of statement that T can be applied to. A, B, and C are going to be variables which range only over Gödel numbers to which T can be applied. Not necessarily is applied, but can be applied. All right. Now, X in those kind of square brackets is the translation of X into a Gödel number in TPA if X is a sentence of TPA. So, using our arithmetization notation from the Gödel numbers video, we can define this as basically, for all X, any statements in our meta language or TPA, the arithmetization of x is that x in the square brackets. Basically, the square brackets translate whatever's inside them to a Gödel number for all x which are sentences of TPA. For example, if we had 0 equals 0 in square brackets, that would be equal to this Gödel number, 808555808, using our previous Gödel notation, representing 0 as 808, equals as 555. Though, as we've noted in our current formulation, that's not exactly going to be what it's represented as. It's actually going to be a list of 808,555,808 S's followed by a 0. Note that the T predicate extends over all of those S's and a 0, or over the kind of square corner brackets over 0 equals 0. But it does not extend over 0 equals 0, since it only applies to Gödel numbers. It doesn't apply to statements that have things like equals signs in them. Hopefully that helps you understand a little bit of what the T predicate, the truth predicate, can extend over, what it can apply to. Now, A, B, and C are going to be variables which range over Gödel numbers to which T can be applied. So using our STTX notation that we just learned, we can define any string which quantifies over a variable A, such as for all A implies A, as for all X, and X can be anything. It could be an object, it could be a sentence, it could be a number, as if X is a sentence that T can apply to, then X implies X. But if it's not, then we're not saying anything about it. So basically, this is only going to function if X fulfills that previous condition. And that previous condition is basically that it is one of these kind of capital letter beginning of the alphabet variables A, B, and C. Or in other words, that it is a Gödel number to which T can be applied. In other words, when you say for all A, B, or C, we are only quantifying over Gödel numbers which create well-formed formulas that T can apply to. They are not making statements about other sentences or objects. We can't universally instantiate something else into those situations. What this means for our universal instantiation rule is that we cannot universally instantiate A as just anything. We only can universally instantiate it as a Gödel number that T can apply to. Or, if we want to instantiate it as anything, we have to use that second formula and use for all X, STTX implies X, because that is only going to give us something real or legitimate if we instantiate it as something that's going to satisfy the antecedent of that conditional so that we can get to the consequent. We will write numbers which have a particular operation added to them inside square brackets. The brackets will be considered to translate anything which is not already a number into a number. Therefore, it's not the case that B, remembering B represents a number, where B is 999 S's followed by a 0, would be the same as 100,999 S's followed by a 0. Why? Because 100 is the translation of that tilde, that negation, into Gödel numbering according to our rule before. So basically, what we're saying is when we have these square brackets around something, we're kind of simplifying the notation. Instead of writing out all the numbers, we're saying that take whatever number is there and translate any symbols that aren't numbers into numbers and put them into that number such that they would create a number that when translated back is going to have that original symbol. This is a notational convention so that we can say things about a number with and without an operation in it, without diving into the kind of mathematical mechanics which make that possible. You could go down and restate this as a mathematical formula of simply adding 100,000 to these numbers or something like that, but it's because we don't need to do that, because we can understand that you could create a mathematical formula such that it would do that. We don't need to put that in our specific formula. Similarly, we could say that B or C in those square brackets, where B is 999 S's followed by a 0 and C is 666 S's followed by a 0, would be the same as 999, which is our representation of or, our disjunction, our V, 666 S's followed by a 0. Tarski proved that we cannot completely define truth within a language. However, we can define truth for parts of the language, and that's exactly what we're going to do. Within TPA, we can define a truth predicate for a sublanguage, namely all statements that are only one number set equal to another, such as n equals m, 2 equals 3, 4 equals 4, and so on. These are atoms of TPA. Remember, atomic statements are kind of those basic statements that other things are made up of. We will call this truth predicate, which applies only to atoms, TO. We could use it to claim that 1 plus 1 equals 2 is true, as follows. TO 1 plus 1 equals 2. Note, it's only applying to atoms. There's no disjunction, there's no conjunction, there's no implication, there's no negation in this statement. It's just one set of numbers set equal to another number. The next step up from these basic atomic true statements is to take any statement which does not contain a truth predicate and claim that such a statement is materially equivalent to the claim that the Gödel number which represents that statement is true. Or in other words, this formula. And that only applies for all x which do not contain a truth predicate. As we just did, creating a sublanguage that a specific truth predicate only applies to things of that sublanguage, we're once again creating a sublanguage saying that this this truth predicate, only applies to not just atomic statements, but now any statement which itself doesn't contain a truth predicate, or a T. So x in this formula cannot contain a T. These are going to be known as T sentences. So basically what we're saying is that it's true that some number which represents the statement x is materially equivalent to that statement x. This may seem familiar, since it is the exact formulation of deflationary theories of truth. It's kind of that disquotational theory of truth. It is true that snow is white, in quotes, if and only if snow is white. Deflationary theories of truth are often paired with axiomatic theories of truth to avoid some of the problems of the liar's paradox in deflation. However, some theorists of truth, and deflationists claim that these T sentences are not sufficient to fully represent truth. One such critic was Tarski himself. According to Tarski, the problem with an axiomatic theory of truth built simply out of T sentences was that you could not, when given a conjunction, predicate truth of the conjuncts. Specifically, you could not prove an analog of the law of the excluded middle. Basically, there's a lot of things that just using these T sentences doesn't let us do. It doesn't let us take things out across a conjunction or distribute a truth across a conjunction. It doesn't let us bring negation in and out of truth, and so on and so forth. It doesn't let us take universal quantification or existential quantification outside or bring them into that kind of truth predicates. We need rules telling us how to use these kind of connexive, these logical operators with truth and bring them inside and outside of truth. Think about it in some ways if you understand modal logic, like the axiom K allowing us to distribute necessity in some way across specific statements. We need a set of rules which lets us or does not let us do that with truth. But before we move on to these additional axioms, which are going to solve that problem and attempt to make TPA more expressive, it's important to note that the T sentences are what's known as conservative over piano arithmetic. What does that mean? Well, conservative over something means that we're not proving any excess theories. The only new theories that can be proven from adding the T sentences are sentences which contain that new predicate, that T predicate. There's no new sentences which only exist in piano arithmetic which don't have that T in them, which we've been able to prove. In other words, the only new sentences that we can prove in PA are sentences which contain the truth predicates. We cannot prove any sentences that do not contain that truth predicate, or that we could not prove which don't contain the truth predicate before. Okay? Basically, having it be conservative over something seems to be a good thing for our theory to do, because it would be strange if simply by adding definitions we could prove new theories which have nothing to do with those original definitions. Okay, so now there are 6 axioms that we'll add to TPA, which to be able to use truth through various logical operators, to kind of solve some of those problems we saw before. We will summarize them briefly here, and then go into greater depth after we explain some notation. The first deals with the truth of atomic sentences. The second defines negation, and deals with truth coming in and out of negation. The third is about conjunction. The fourth regards disjunction. The fifth explains universal quantification, and the sixth explains existential quantification. All of these axioms are very intuitive, and they'll follow kind of what you expect them to follow. But we'll go through them to really understand kind of the logical framework supporting them, and especially to get the notation, which is going to be very important when we move forward to the type-free theories of truth. So, speaking of notation, before explicating these in greater depth, we need some new notation. So, the first piece of new notation that we're going to add is ATPAA. So that's going to say basically that A is an atom. It's just a number equals a number of piano arithmetic. Basically TPA without the truth predicates. So A is going to be an atom, or the number that A represents is going to be an atom of piano arithmetic. STPAA is saying that A is representing a sentence of piano arithmetic. Once again, that's without any of the truth predicates. So we're using these to kind of define that sublanguage, to section out these things. The first really small sublanguage of just the atoms, and then the slightly bigger sublanguage of the sentences, which don't include the truth predicates. AX means that A is an open formula, and X is the only free variable. Basically, that means that X is present in A as a variable, and is not universally or existentially quantified over. For example, A, when translated, could represent the sentence, there exists some Y such that X equals Y. You see that Y is a bound variable. It's not a free variable because it has that existential quantifier in front of it out front. But X is a free variable because there's no existential universal quantifier out front. So that variable is free in this A. So AX is another way to represent that. A is an open formula with X as the only free variable. AX in the square brackets with the underline under the X means that X is bound from the outside. Or in other words, there is a free variable in the translation of A. So those square brackets have translated everything. That variable is bound by a quantifier, which is in fact outside of the square brackets. As in, for all X, square brackets, AX with the underline under it. The point is, the reason we underline it is to show that it was a free variable inside that formula, but outside of those square brackets, it became bound by some universal or existential quantifier. All right? If those didn't make too much sense right now, we are going to give specific examples when we get to the axioms. STPA for all X. A can be translated as AX is a sentence of piano arithmetic and has at most one variable, namely X, free. And that should just be kind of defining exactly what we're talking about when we're talking about that statement, AX. We will work through all of this new notation as it comes up with each of the axioms. So don't fear if you're having a little bit of trouble right now. It will also be very important as we move forward into our videos on type-free axiomatic theories of truth. So I encourage you, if you have trouble with those videos, come back to this notation because it will help you. Now, on to the axioms. So the first axiom states that for all numbers that the truth predicate could apply to, remember the truth predicate applies to numbers, not statements, if that number represents an atom of piano arithmetic, then T applying to that atom is materially equivalent to TO, the predicate, which only deals with those kinds of statements of the number equals number, applying to it. Basically, it's stating that atoms must be true by the standards of numbers alone, numbers equaling numbers to be true. And that's the only way that they can be true. And if they're true by that, it's both necessary and sufficient for them to be true by our larger truth predicate, just T. The second axiom is going to be important as we move forward into type-free theories of truth, because it's talking about negation and what we can do relative to negation inside and outside of truth. It claims that for all numbers A that the truth predicate could apply to, if A is a sentence of piano arithmetic, then the truth predicate applies to the number A with the addition of the representation of negation at the beginning of it. So that would be like adding that 100 in front of whatever number A is, if and only if it is not the case that the truth predicate applies to that original number A. In other words, what we're saying is negation can be taken into or put outside of the truth predicate's scope. It is true that A is not the case if and only if it is not true that A is the case. This should be very intuitive with our idea of the way that truth and negation work. But as we move forward into type 3 free theories of truth, we'll see that it may not be as intuitive as you thought it was. The third axiom is going to deal with conjunction. It's going to be kind of our distribution across conjunction axiom. It claims that for all numbers A and B, which the truth predicate can apply to, if A and B represent sentences of piano arithmetic, then the truth predicate applies to the numbers A and B with the numerical representation of conjunction in between them, if and only if the truth predicate applies to A and it applies to B. So basically, our truth predicate applies to that conjunction, and it's in those square brackets, square bracket A and B, close square bracket, because that and is not actually part of that number. It's actually one long number that starts with all the digits of A, the digits of conjunction, and then all the digits of B. But what we're saying is that can actually be translated as pulling that conjunction out and just having the truth predicate over all the digits of A, the conjunction outside of the scope of the truth, and then the truth predicate over all the digits of B. Effectively, T can be distributed across conjunction and pulled out from a conjunction when it's in the form of a numeral. A and B are true if and only if A is true and B is true. Once again, the basic idea is really intuitive. The way that it has to be framed to get through all of these kind of problems that arise with the liar's paradox creates a lot more of the confusion. So, the fourth axiom is going to deal with disjunction, and it's very similar in form to the conjunction axiom. It claims that for all numbers A and B, which the truth predicate can apply to, if A and B represent sentences of piano arithmetic, then the truth predicate applies to the numbers A and B with the numerical representation of disjunction in between them, if and only if the truth predicate applies to A or it applies to B. This is basically the same thing we did with conjunction, but instead of putting conjunction in, we've put disjunction in. So instead of having a bunch of numerals, the numeral for conjunction, and a bunch of other numerals, the first one representing A, the second one representing B, now we have a bunch of numerals representing A, the disjunction numeral, and then the bunch of numerals representing B. And we then split those up and put the actual symbol for disjunction in between them. So in other words, truth can be distributed, or T can be distributed across disjunction and pulled out of a disjunction when in the form of a numeral. A or B is true if and only if A is true or B is true. Now things are going to get a little bit more complicated. The fifth axiom deals with universal quantification, and here's where we're going to use some of those kind of strange new notation pieces. It claims that for all open formulas, remember that open formula is saying that x is not bound in the formula A, that T could apply to. If AX represents a sentence of TPA, then the truth predicate applies to a number representing the universalization over X in AX, if and only if, for all Y, T applies to the open formula AY, where Y is bound by the universal quantifier from outside. Basically, you can bring the universal quantifier out of or put it into a truth predication. If you look carefully, you'll see that all we've done is, once again, inside the square brackets, you have the universal quantification over X of that bound variable in that A. And we're going to pull that out of the formula, and we're going to throw it on the outside, and then bind that new variable Y from the outside. The simpler way to think of this is you can pull universal quantification outside of the scope of the truth predication. And the same is going to apply to existential quantification. It claims that for all open formulas AX that T could apply to, if AX represents a sentence of PA, then the truth predicate applies to a number representing the existential quantification over X in AX, if and only if there exists a Y such that T applies to the open formula AY, where Y is bound by the existential quantifier. In other words, once again, you can bring the existential quantifier out of or put it into a truth predication. And remember, when it's inside those square brackets, it's not actually listed as existentially quantified X. It's a bunch of numbers that represent that, next to a bunch of numbers that represent a formula with a free variable. Okay? So, those were our 6 axioms. Now, we're going to take a moment to step back and remember our piano arithmetic. So, if you remember, the fifth rule, or the fifth kind of piano postulate, was the principle of mathematic induction. As it has been stated so far, the principle of mathematical induction does not apply to statements with the truth predicate in them. So long as we keep these separate, these new axioms are conservative over piano arithmetic, remembering that conservative means they do not prove any new theorems which lack a T, which is good. But if we allow the use of induction with the T predicate, we are no longer conservative over piano arithmetic. But we can prove some interesting consequences. One thing we can prove is something known as the global reflection principle. So why would we want to expand the reach of the induction axiom if it's going to prevent the system from being conservative over piano arithmetic? It seems to make sense that we want our system to be conservative over the original kind of base theory, because otherwise that means just by defining truth, we're adding kind of new rules or new true statements which have nothing to do with truth. Because it will mean that we can prove useful things like the global reflection principle. We're not going to go into the global reflection principle too much here, but basically it guarantees the soundness of the system. Basically, it claims that if you can prove something in the system, then that must be true. Now, before we go, let's talk a little bit about hierarchy. So if we want to talk about the truth of statements which do possess a truth predicate. So remember, all of our axioms just applied to the original statements of piano arithmetic. They weren't any of the statements of TPA. They weren't any of those additional statements which had truth predicates in them. We only need to create a hierarchy of truth with indexed truth predicates. So we'll call that truth 1, and then we'll have a truth 2, which only applies to those, and a truth 3 that applies to truth 2, truth 1, and so on and so forth. Each of the truth predicates can only apply to sentences with truth predicates of lower value. For more on this hierarchy, check out Tarski's hierarchy of languages because it's very similar. It's just kind of a different approach and coming from a different direction. Coming from, once again, the axiomatic direction as opposed to the semantic direction looking at meaning. Overall, the typed axiomatic theory of truth will run into many of the same problems that Tarski's hierarchy of languages did. It just kind of explains it in a different way. Type-free theories of truth, on the other hand, may be able to avoid some of these problems, but they're going to, in turn, encounter some of their own. So up next, we will be looking at type-free axiomatic theories of truth. There's two we'll be looking at, FS for Friedman-Schier, and KF for, finally getting to Kripke-Pfefferman. Watch this video and more here at Carneades.org, and stay skeptical, everybody.